So welcome to the 86th Theoretical Physics Colloquium by Dvali, who's a Humboldt professor and a chair at Ludwig Maximilian University in Munich. He is a director of Max Planck Institute of Physics in Munich as well. He received his PhD in 1992 from the Institute of Physics of the Georgian Academy of Sciences. After that, he had two postdoctoral positions at ICTP in Trieste and INFN in Pisa. And after that, he became a scientific associate at CERN in 95. Since 97, he had a tenure track position at ICTP in Trieste and then became a faculty at New York University. In 2004, he became a full professor, and in 2006, he was silver professor of physics at New York University. Since 2007, he was also a member of theory group at CERN until 2012, and he became the director of Max Planck Institute back in 2009, and he remains the director now. He's a Humboldt professor and a chair at Ludwig Maximilian University in Munich since 2019. Over the years, he received a number of recognitions and awards. In 1999, he became David and Lucille Packard Fellow. In 2000, Alfred Sloan Fellow. He received a New York City Mayor's Award for Excellence in Science and Technology in 2001. Distinguished Research Chair at Perimeter Institute in 2008 and Humboldt Professorship in the same year. In 2014, he received Severo Ocor Distinguished Professorship at IFT Madrid and Lawrence Professor in Leiden in 2020. His research interests are very wide: general relativity, particle physics, cosmology, quantum gravity, large extra dimensions, black holes, and many other things. And today he will be talking about demystifying black holes. And with that, I'll give the microphone to Gia.
Thank you very much. I hope you can hear me. Thank you very much for the invitation. A nice introduction. It's a great pleasure to give this talk. And so I will share some ideas about black holes. So it will be based on a number of papers, on series of papers. And so the concept was introduced in this paper here, but was based on earlier work. And then I will also base my talk on papers done in collaboration with Otari Sahelashvili, Oleg Kaikov, Juan Valbuena, Florian Kuhnel, and Michael Zantedeschi. I will briefly mention, but also the work done in collaboration with Raju Venugopalan about color glass condensate in QCD. So let me start. So black holes are considered to be mysterious because of good reasons. And there are certain properties of black holes which are commonly accepted and are considered to be very interesting and in a sense mysterious. So, for example, black hole is classically stable, quantum mechanically decays by Hawking radiation, by Hawking process, but decays in a very interesting way, radiating in a spectrum which is nearly thermal and with temperature given by the inverse size of a black hole. So black holes also carry entropy, actually huge entropy, with the entropy which scales as area in units of Newton's constant. So that's also considered to be mysterious, the area scaling of the entropy. Another mystery is that, so you have this object that carries enormous microstate entropy, so it carries an enormous amount of quantum information, and it decays, but releases information extremely slowly. So at the initial stage, it basically releases no information. And there is a common agreement that there is a minimal timescale for the start of the information retrieval, which is given by so-called pages time, which you can write in several different ways. You can write it as an entropy times the radius, or you can write it as volume divided by Newton's constant, and so on. Okay. And so as I said, if there will be some short urgent questions, please, you can just speak up. So there's no, don't hesitate. So now what I want to show in this talk is that these seemingly mysterious properties of a black hole, they are shared by objects that have, it's a wide class of objects, large class of objects that have maximal entropy and maximal information capacity compatible with unitarity. Now, why is this important? Because often we assume that these properties that black holes have, that I've listed, they originate from gravity or even quantum gravity. But what I want to show is that actually there are objects that carry identical properties and which have nothing to do with gravity. So I call these objects Saturons, because they saturate the capacity of entropy or capacity of information storage, which is permitted by unitarity of the theory. Now, under entropy, I will very rigorously define entropy as logarithm out of number of degenerate microstates of the system, all states being pure. So it's an invariant definition. Invariant notion. Now, what is very interesting is that these objects, these Saturons, saturated objects, which behave like black holes, they exist in renormalizable theories, also in renormalizable theories, in calculable renormalizable theories. So basically, what emerges is that black holes are one representative of this large class of objects, of states. Saturons. So sometimes we call black hole Saturon correspondence. So let me discuss a little bit a strategy. Okay, now when we encounter a mysterious phenomenon of nature, let's say, I don't know, there's a bucket of water, water evaporates, and we want to understand what is this substance. So there are at least two approaches to the problem. So the first approach is that we go ahead and create a microscopic theory. Okay, for example, we give a corpuscular resolution of water in terms of molecules. So we formulate the microscopic theory, and then we show that this theory somehow explains properties of water, and it also predicts some new phenomena. Now, I have taken this approach to black holes together with my collaborator Cesar Gomez some time ago. But in this talk, I will try to distance maximally from offering any microscopic explanation or any microscopic theory of a black hole. Maybe at the very end, I come back when I offer an interpretation in terms of this theory. But the bulk of the talk will be based on a different strategy. And the strategy is the following, the second approach. So you have this bucket of water, but you don't try to come up with microscopic theory. Instead, you try to see if the phenomena repeats itself in other systems of nature. So if you discover that there are other systems of nature that have similar properties, then this allows you to understand properties of water in terms of some universal underlying phenomena, which are not particular to waterness. Okay, and so this is the approach to a black hole that I will discuss in this talk. Okay, and so now the idea is that, okay, so I want to understand, basically the question that I'm trying to pose is, how special are black holes? Okay, Of course, we know black holes are special, obviously. For example, we know that if I take an apple and I compare apple with a black hole of the same size, of course, these two objects are very different. But that's not a very informative statement, because to compare objects, we have to bring them within certain measure, within certain universality class. So the correct question that I will ask is the following: that how different an apple would be, apple or any other object, would be from a black hole if apple would have a maximal capacity, maximal entropy compatible with unitarity. Now, of course, we need some underlying fundamental principle that is more powerful than gravity, because we want to go beyond gravity, right? And so the universal underlying principle I chose to be unitarity, because that's the most fundamental principle that, I mean, the theories that make sense, they cannot violate unitarity. They must be unitary. So unitarity is above everything. It's above gravity, above QCD, above QED, above. And so this will be the guideline. So for me, the guideline will be unitarity and the maximal entropy compatible with unitarity, maximal microstate entropy. Okay. So this is the idea. And so here is a bound, okay, that I propose that. So the bound, again, must be formulated in terms of universal parameters, which are not specific to gravity or QCD or to any other theory. And here's the formulation of the bound. So there is, let's say we have an object of, you have a self-sustained object in whatever theory, with gravity, without gravity. Sure, yeah.
We have a question.
Yes,
yes,
sure.
Sir. So what do you mean by the unitarity of the model? That is it related to the matrices or of the operators involved in the theories?
Right, my whole talk is about that. So, so the unitarity, I mean that. So there is a. So let's take an apple. So you take an apple and you arrange your apple in such a way to have maximal capacity of information storage. You can do this by changing parameters of the apple. You can change mass, coupling constant, strength, size, and so on. Or you can also change parameters of the theory.
Yeah.
At some point, an object of that size will have entropy beyond which you cannot go in a unitary theory. Okay, so that's what I mean under unitary. Of course, you cannot violate unitarity.
Yes, sir. So in terms of gravity, this unitarity, how does it enter in that? Because in gravity, at least in general relativity, we are dealing with metric and which are basically functions.
No, I don't say. I mean, gravity must be as unitary as any other theory. I mean, non-unitarity theories that are not. So in other words, I'm not interested in theories that are not unitary, because I don't even know what to do with them. So therefore, so if your question is, so I don't know whether your question is that gravity may not be unitary.
Let me elaborate my question, sir.
Maybe we should keep this until the end, because it's turning into a discussion rather than a short question.
Okay.
Yeah, right.
Okay.
Right. So in other words, just to anticipate, so the unitarity is the most fundamental principle of physical theories, or at least one of the most fundamental principles. Theories that are not unitary, I'm not interested in those theories. Okay, there is absolutely no evidence, or the theory of gravity, of course, must be unitary, just exactly as it is, as we know it is. As we know, gravity is a unitary theory. Fortunately, of course. But how the unitarity affects the entropy, this is the key point of my discussion. Okay, I'm not even questioning the theory must be unitary. Okay, that goes without saying. But it's very important to understand how unitarity translates in the bound on entropy. Okay, so for this, let me first formulate the bound on the entropy. So what is the bound? So the bound is this: if you have an object, a self-sustained object, I don't know, could be a bucket of water, could be a black hole, could be a magnetic monopole, whatever, soliton, whatever you want. which has certain size, characteristic size R. So the maximal entropy that this object can have in a unitary theory is given by this formula. What is this? This is area of the surface area of this sphere of radius R divided by the coupling of a Goldstone boson. So what enters here, all Goldstones count that emerge as a result of spontaneous breaking of symmetry by this object. And I will explain this in great details. So the area, of course, is something that scales as the radius in power d-2. D is the number of space-time dimensions. And G, gold is the Goldstone coupling. Okay? So now, the Goldstone coupling, of course, has dimensionality, and dimensionality of the Goldstone coupling depends on the number of space-time dimensions, obviously. So, for example, in 3+1, Goldstone coupling has dimensionality of inverse mass square. So instead of Goldstone coupling, we can trade Goldstone coupling for Goldstone decay constant, which I will call F. In 3+1 dimensions, Goldstone decay constant has dimensionality of mass. And we can also form a dimensionless coupling of the Goldstone boson. So this is the dimensionless coupling. Now, dimensionless coupling, quantum coupling. The couplings, they run, obviously, they depend on the scale. The couplings depend on the scale. They depend on the momentum transfer in the process. So this dimensionless coupling, which I call alpha, controls the scattering of Goldstone bosons, okay? 2-to-2 scattering, for example. At the momentum transfer 1/R, okay? So it's the dimensionless coupling evaluated at the scale R. Now, this dimensionless coupling is given by Goldstone coupling divided by the area of scale R. Now, this is something very interesting, but I've never seen this paid attention in the literature previously. So the fact that Goldstone coupling scales as area, as inverse area in arbitrary number of dimensions. This is simply a fact of, I mean, this comes from Goldstone theorem, okay? It's an observation, but it will turn out to be an extremely important observation, okay? So therefore, entropy bound, you can formulate in two equivalent ways. So this less than the dimensionless coupling, 1/dimensionless coupling, or the area divided by the Goldstone dimensionful Goldstone coupling. Of course, these two are the same thing. Okay, so now we can ask this question, where are the Goldstones coming from, right? And the Goldstones are coming from the fact that an arbitrary object that can store quantum information, or an arbitrary object that can have microstate, degenerate microstates, always breaks spontaneously some symmetries, okay? There is universally spontaneous breaking of Poincare symmetry. And the G gold, and the coupling of the Poincare Goldstone boson is unambiguously defined. So there is no ambiguity in it. If you give me an object, we know what is the coupling of the Goldstone boson of broken Poincare symmetry. Quick
question.
Yes.
In gravity, what are the Goldstone bosons you have in mind?
For example, for a black hole, so black hole obviously breaks Poincare symmetry spontaneously. I'm considering black hole on asymptotically flat space. So that breaks Poincare symmetry spontaneously. And the order parameter of that symmetry breaking is the expectation value of the graviton field. Now, of course, graviton field is gauge dependent, but that's not a big complication. We can always, in any gauge, define this order parameter. And correspondingly, the decay constant of the Goldstone boson of broken Poincare symmetry is Newton's constant itself. Okay, and that's actually very, very useful question that you're asking. That usually I'm getting this question towards the end of the talk, but this is very important because, and this is a property of arbitrary black hole of arbitrary size. Now, the way you can understand this is the following: that if I'm taking a black hole of arbitrary size, and I'm an observer at infinity, and I'm approaching a black hole from infinity, the Newtonian component grows and reaches the maximum at the horizon. And that maximum for the canonically normalized graviton field is always the Planck mass. Okay, so basically, there's a universal statement that canonically normalized graviton field always reaches Planck mass at the horizon. Okay, so that's why the Goldstone decay constant is given by the Planck mass. Okay, for a black hole universally. So that will also explain this connection that I'm suggesting. So now, for example, in general, if we have for example, a bound state of n quanta, so imagine that you have some kind of standing wave or a bound state of n quanta of wavelength r and frequency 1/r. So we can derive this Goldstone coupling constant very easily, and actually it scales as 1/n times the area. Now, in general, the states with high entropy, they also contain other Goldstone bosons. But the Poincare one is the most important one because that's universal. Okay, so that's just across the disciplines, across the theories. So therefore, objects of maximal entropy, their entropy is given by this: 1 divided by alpha, where alpha is dimensionless coupling of the Goldstone boson, or area divided by the coupling of the Goldstone boson. And as I said, I call them Saturons. We call them Saturons, and okay, so these are the objects. Now, it turns out that there is also a universal bound on the time scale of information retrieval from a Saturn. Because you have this object which has maximal entropy compatible with unitarity. And now you can ask this question, okay, there is this object, and it encodes quantum information because it can be in exponentially large number of degenerate microstates. And how long does it take to retrieve this information? And there is a universal bound on this, again compatible with unitarity, again constrained by unitarity, which is given by the size of the object divided by alpha, the alpha that I gave, okay? And because of saturation, it can also be rewritten in several equivalent ways. For example, it's also entropy times the size of the object, or the volume in units of Goldstone decay constant. Okay, and as you can already see, these are strikingly similar to pages bound. These are identical to pages bound for a black hole, for pages time for a black hole. So now the interesting thing is that all Saturons, they have properties that are very similar to black holes. This is what we are discovering. So not just entropy and information retrieval time, which I already discussed, so area low entropy, but also their evaporation is nearly thermal with temperature, which is strikingly similar to Hawking temperature. They, semi-classical, they have information horizon. And as I already said, time of information retrieval is like pages time. They saturate scattering amplitudes, unitarity of scattering amplitudes. And I will also discuss they have very similar bound on the spin. Very similar to a black hole. Okay, so the way I decided to structure this talk is that I will give you a simple prototype model, and I tried to adjust this model in such a way that this can be user-friendly for people interested in different systems. Okay, so sort of to have this model that captures maximally general features. So in order to have a Saturn system with Saturons, of course, we need a field, certain order parameter, a field. And so I chose this to be a scalar field, transforming as an adjoint representation of certain SUN symmetry, global SUN symmetry. Now, the precise representation is not so important. You can take any other representation. It's very simple to work with adjoints. Everybody is familiar with adjoint representation. And so basically phi is an n times n Hermitian matrix with 0 trace. Now we can think of phi as prototype for many systems. In what I will say, phi serves as a prototype for many systems. For example, if you are a QCD person, you can think of phi as pion field for large number of flavors, okay, or even a gluon field for large number of colors, or if you want to use this in many-body physics, you can think of this as Gross-Pitaevsky field of some many-body system, okay? So it's very general, but so I will limit myself with most general renormalizable theory, because that's the most interesting one, right? Because the renormalizable theories are thought to be most distant from gravity. That's why I'm choosing renormalizable theories. So we take a most general renormalizable theory of this field phi. So it contains a kinetic term and a potential. So again, I'm writing potential to be most general renormalizable potential. The only thing I'm doing, I'm arranging it as a perfect square, as customary, because it's easier to work with potentials that are perfect square, but it's not necessary. Just for illustrative purposes, it's just useful. Okay, so the theory contains two parameters. So one is the coupling constant, alpha, okay? This is fundamental coupling constant. And another is the scale f, okay? So it's a very simple theory. Now the fundamental coupling constant, this controls the 2-to-2 scattering amplitudes between phis, between fields, right? And this coupling can be taken arbitrarily weak. So not only that I'm working in renormalizable theory, but I'm also taking coupling to be arbitrarily weak. Actually, you can even take coupling in the double scaling limit when coupling is 0, but yet theory is non-trivial because unitarity is controlled by a collective coupling, alpha times n. Now, for those of you that are familiar with QCD, large N QCD, with large number of colors, you will immediately recognize Toft coupling. So this is a sort of a Toft coupling, okay, for this theory. Of course, here we don't have QCD. It's just it's a very simple theory, but it's the same nature, the coupling. Now, unitarity constrains this collective coupling, and this is very important. This has to be paid very close attention. The Toft coupling is restricted by unitarity to be less than order 1, okay? So Toft coupling cannot be arbitrarily large. There are several ways how theory tells us that. Here, it is sufficient that I'll just notice that there are certain number of loop diagrams that represent expansion in the collective coupling. For example, bubble diagrams like this, they represent expansion in collective coupling. So each bubble adds a factor alpha n. Why? Because there's alpha from coupling, and then there are n flavors running in the running in the loop. Okay, and correspondingly, you can see you see immediately that if alpha n exceeds 1, this expansion breaks down, and series have to be resummed. Now, of course, you cannot violate unitarity of the theory. This is very important to understand. Maybe this also connects with the previous question. So if I give you a renormalizable theory, whatever, this theory is unitary. I give you Hamiltonian theory is unitary. Now, what will happen in the theory instead if you try to go into the domain where Toft coupling is strong, is that theory will change a regime. So your field phi will no longer be a good degree of freedom. Instead, you will go into new degrees of freedom, okay? So that's what will happen. And so what we are observing is the following thing, that if you have a bound state and you try to push the entropy of this bound state past the bound that I gave you, what happens is that necessarily theory changes the regime, and in new degrees of freedom, the entropy actually decreases. Okay, so the entropy reaches maximum. If you push it further, then it decreases because theory rearranges itself. So it's a very interesting effect. So now, the analysis also, sometimes people like to use this double scaling limit. Sometimes we call it Toft limit, where you can actually take alpha to be exact 0 limit and n to the infinity and keep alpha n finite. Okay. So in this limit, the analysis simplifies enormously. So it's very nice. We can use the power of large n for solving the theory. Okay, so now I want to show that this simple theory, renormalizable theory, arbitrarily weakly interacting, turns out not to be so simple, because it gives saturated states which exhibit all the properties of black holes. Okay. Now, in order to show this, I first specify the vacuum. Okay, so we need to specify vacuum. So we solve vacuum equations. Since I gave you potential to be perfect square, vacuum equations are also very simple. They are simply quadratic equations, because the vacuum is where potential vanishes, and so it gives you, this effectively gives you a quadratic equation for phi, which is easily solvable. And for those of you that are familiar with supersymmetric random unified theories, this technique is very well known there. Okay, so you can solve this equation, and you discover that there is a multiplicity of degenerate vacuum states, but I will focus only on two. So I will focus on the vacuum SUN, symmetric one, where the expectation value of field phi vanishes. Okay. Now, in this vacuum, symmetry is unbroken, and there is a mass gap. The theory has a mass gap, okay, which is given by square root of alpha times f. There is another neighboring vacuum separated by a barrier, potential barrier, in which symmetry is spontaneously broken down to a SUN minus 1 cross U1. So the expectation value takes this form, it's split in this way. Now, in this vacuum, in this neighboring vacuum, there are of order n Goldstone bosons, couplets Goldstone bosons. So there are two vacuum coexisting, one with mass gap and the one with Goldstone bosons, couplets. Okay. Now, this vacuum actually can coexist in real space. I mean, Tanmay knows this very well. So they are separated by, in that case, they are separated by domain walls. Okay, and for a flat wall, you can even write the solution. It's very easy to find the solution. So, for example, here is the example when we have on minus infinity, we have SUN symmetric vacuum. In plus infinity, we have SUN minus 1 U1 symmetric vacuum, and they are separated by the domain wall, which is given by this 1 plus tangent hyperbolic. The modulus changes, and the wall thickness is given by the Compton wavelength of the quanta in the unbroken vacuum. Okay. However, this is not the configuration that we are interested in. We are interested in a configuration in which there is a unique vacuum at asymptotic infinity. Okay. So the configuration is we choose SUN symmetric vacuum as our vacuum. Everywhere at infinity, we have a SUN symmetric vacuum. So we have an observer. Here's the observer, Alice. And this observer can, Alice is an asymptotic observer, and she can classify all objects according to representations of this SUN group. So it's a very powerful symmetry classification that you can use. And in this vacuum, we embed a bubble of a vacuum of the broken phase. Okay? So now we have a bubble, and inside this bubble, the symmetry is spontaneously broken down to SUN minus 1 cross U1. So the bubble profile is like this. Okay. Okay, so now what is happening? What is happening is the following thing, that in asymptotic vacuum, we don't have any Goldstone bosons. The theory has a mass gap. But theory of a bubble has huge number of gapless modes. And because of this, there is an enormous microstate degeneracy of this bubble. So what Alice sees that the bubble transforms as a huge exponentially large representation of the group and has a very high microstate entropy. So literally what Alice can do, she can encode quantum information in the excitations of the Goldstone modes, in the gapless excitations of the gapless Goldstone modes in the bubble.
Excuse me, Gia, but
yes.
If they are degenerate, the vacuum energy densities are degenerate, this bubble will tend to shrink, right?
Yeah, exactly right. I'll get there. Yes, of course. Right. So therefore, obviously, so as Misha commented absolutely correctly, So if the Goldstone modes are not excited inside the bubble, okay, so what will happen is that the bubble will shrink, okay, will shrink, will oscillate, and then dissipate. Even while bubble is shrinking and oscillating, it is still an exponentially degenerate state. So therefore, the fact that bubble shrinks doesn't change the fact that it still carries enormous entropy, okay? So, however, we prefer to work with bubbles that are classically stable, okay? And what happens is that bubble can be stabilized precisely by the excitations of the Goldstone modes. So what happens is that if you excite Goldstone modes, they stabilize the bubble. The quantum information, which is carried by this Goldstone mode, is stabilizing the bubble. Now, when occupation numbers, because occupation numbers are large, this stable bubble has a corresponding classical description. So we can find a classical solution for it. And there is a classical solution that you can construct. For those of you that are familiar with so-called non-topological solitons or cuboles, this state is sort of shares some similarities with cuboles. Of course, cuboles are not saturated states normally. So you can think of this as sort of a type of a cubole that is saturated. But the techniques of why it is stable is similar, because what you do, you rotate the bubble, you excite Goldstone bosons, and excitation of the Goldstone boson means that the bubble is rotating in the internal space. It's not spinning in the outer space, but it is rotating in the internal space. And so this is the configuration. The configuration is the profile of rho has this profile. R is the radius of the bubble, and T is one of the broken generators. Now, what you can do, you can first construct this solution for one particular broken generator, and then of course, any solution that is obtained by SUN transformation is also a solution, obviously, because of the symmetry of the problem. Okay. So therefore, you have this exponentially large number of degenerate solutions, okay, corresponding to different orientations of these Goldstones, and the bubbles are stationary and stable. The radius is expressed in terms of mass and the frequency, okay, and the occupation number of Goldstone modes scales as this: is 1 over alpha times m divided by omega in power 5. Now, I want to share, of course, everything can be done analytically. It was done analytically, but it's always good to watch some movie, a numerical simulation. So let me share this, unshare and share this numerical simulation because I have it in a separate file, just for fun, okay? Let me. Okay, now let me share this numerics. Okay, let me share this first. You see the file, right?
Yep.
Okay, so this is an example of precisely what Misha said. The bubble that is with unexcited Goldstones, which collapses and dissipates. Okay, so let me do it again. Okay, so the bubble shrinks, collapses, dissipates. Now, dissipation time can be pretty long in general. Of course, here in numerical simulation, it's not very long, obviously. Okay, now let me share the case with the stable bubble. Let me share the other one. Okay, so now here we have a bubble in which Goldstones are excited. And so what happens is that the excitation of the Goldstone stabilizes the bubble. Now, this is a very beautiful phenomenon. Why? Because think in terms of quantum information. So what happens is that because we have excited Goldstone bosons, there is quantum information carried by them. This information cannot be released because if bubble collapses, this information has to be released to the asymptotic infinity. But that's very costly in energy because there are no Goldstone bosons that live outside of the bubble. The area outside has a mass gap, okay? So correspondingly, what happens is that the bubble locks itself thanks to the quantum information that it carries, and simultaneously, it forms a horizon for quantum information. Because since quantum information is encoded in Goldstone flavors, for example, here, this is bubble, not just that is in its ground state, but excited bubble. Okay, and this excited bubble, information cannot go out because precisely of this phenomena. Okay, of the fact that the information carriers are locked inside by the horizon. Okay, this already sort of gives some glimpses of black hole type behavior as far as quantum information is concerned. Okay. Okay, let me go back to the let me share the talk. And I have to. Okay, so now it works. Sorry. Okay, so this is the point, right?
Oh, sorry, quick question.
Yeah, sure. Yes, please, please.
So the Goldstone bosons can't escape, but there must be some exponentially small leakage.
Yeah, I will discuss leakage. So there is a quantum leakage for sure. At large n, the most important is the quantum leakage, okay? Which actually is not exponentially small, but it's like Hawking. It's very similar to Hawking. It's not exponentially small, it's 1 over n effect, okay?
Okay.
Actually, it's larger than exponential, but the remark is in absolutely in right direction. So now the energy of the bubble scales as occupation number of the Goldstone modes. And level n has microstate degeneracy, which is given by this number of states. I have used the Stirling approximation here. And there is a corresponding microstate entropy. Okay, so now we can ask this question. Okay, so Alice is observing this bubble. And now Alice wants to understand for a given size, what's the limit of the entropy that Alice can give to this bubble, okay? By dialing up parameters of the theory, okay? Now, naively, it looks like Alice can make this entropy arbitrarily large because it's proportional to n, and Alice can simply dial up n, okay? But there is no free lunch because of unitarity. Because if n goes above critical, then the theory will change the regime, and so the bubble simply will stop to exist. Okay, so now let's find out the saturation. Where does the bubble saturate the bound on entropy? Okay. Now, and compared to the bound that I've listed. Now, there are two types of Goldstone modes in the bubble. There is a Poincare Goldstone. So Poincare Goldstone, coupling of Poincare Goldstone is given by this formula, omega squared divided by m to the 4. It has dimensionality inverse mass square. And there is a dimensionless coupling of Poincare Goldstone, which goes like this. There are also internal Goldstones. Their couplings correspondingly are given by these formulas. Okay, so this is dimensional coupling and dimensionless coupling. So entropy, according to what I told you, unitarity would tell us that entropy within the validity of the bubble solution cannot exceed either of these two. Okay, so we have this bound on entropy. Now, this is the bound on the entropy of a state. But on top of that, there is a general bound of unitarity of the theory, because theory tells us that if you want your phi's to be your degrees of freedom, you better respect this bound. Okay, now if we put everything together, there is something very interesting coming out, that the saturated bubbles, they have all the scales and all the occupation numbers equal, okay? So the saturated bubbles are the ones for which the oscillation frequency, the mass gap, and inverse size are the same, and occupation number of Goldstone modes, actual occupation number of Goldstone modes, matches the number of Goldstone flavors, okay? So we have to distinguish these two numbers, because number of Goldstone flavors is n, the occupation number is little n. So you can have situation when only one flavor is occupied, or you can have situation where many flavors are occupied, okay, with the same total occupation number. And the occupation number is given by 1 over alpha. Now, at the saturation point, all the Goldstone couplings become equal. So the Poincare Goldstone and SUN Goldstone couplings become equal, their scales become equal, and also dimensionless couplings become equal and become 1/n. So now you see why this is important, why I'm making a accent on this. This explains why saturation is such a powerful phenomenon, because this tells you that you can have theory which contains many different parameters, but the saturation point is the point where theory becomes extremely simple. I mean, in other words, not theory, but the object becomes extremely simple because it takes place for these very special values of these parameters, okay? And this is the key, all right? So now, what are the parameters of the Saturon bubble? Saturon bubble has entropy very similar to a black hole. Now already, Igor asked this question about the Goldstone. What would be Goldstone for graviton? Goldstone decay constant for graviton. Goldstone coupling constant for graviton for a black hole is Newton's constant. For a black hole, of course, only is Newton's constant. And correspondingly, therefore, both entropy and the mass, they obey exactly the same relation as black hole entropy and the mass. Okay. Now, let's go further. Now, it turns out that not just entropy, but also the decay, and here's this goes to Tame's question. So the saturated bubbles, okay, they decay with the process, with the decay with this. Okay, here is something very interesting, okay, because you have a pure state, no gravity, no non-renormalizability, nothing, okay, pure state, all right. And this pure state simply decays as it should. But it decays in such an interesting way that it confuses you with the thermality, with thermal decay. So impression is as if the spectrum of decay is thermal with the temperature given by the inverse size. And let me explain why, okay? Now, here is a typical diagram of the decay, okay? So what happens is that the initial bubble, so here, of course, I have introduced some spectator representation, massless fields, just repeating the same what Hawking did in a different language. So introducing some spectator field, some probe field, psi. For simplicity, I took fundamental representation. It's not so important in which representation you take it. And so there is a decay of flavor. So these colors, they denote flavor quantum numbers that psi's are taking out of the bubble, okay? So bubble emits psi's and decays. Now the decay rate is exactly because of saturation, because of this alpha n equals 1, and because of saturation of the state, the decay rate is given exactly by the Hawking rate. It is given by 1/r, okay? The decay rate. So this is like literally like a Stefan Boltzmann law for a black hole, okay? So then what happens is that you have high order.
Excuse me, may I quickly interrupt?
Yeah, of course, sure.
When this bubble decays, outside the bubble, there is no gapless state, right?
No, I said I've introduced the gapless states, this size.
And then you couple them to which degrees of freedom?
To phi. I just introduced some.
Okay, you introduced psi by hand and then wrote a coupling, some coupling between phi and psi. Okay.
Right, I wrote a coupling, but of course it's very important. I wrote a coupling compatible with unitarity. So I wrote a coupling compatible with unitarity. However, I want to comment that actually it turns out that even if you don't introduce phis, I just introduced psi's because of illustrative purposes, because it's easier to analyze in that case when you have a ready-made massless field. Why? Because I simply wanted to imitate Hawking's computation, and Hawking is doing computation for a massless field. However, it turns out that you don't even need that. It turns out that because the size of the saturated bubble is given by the Compton wavelength of the quanta in the exterior, there is decay also in the massive modes. Okay.
Okay.
Okay. So, but here it's just simply cleaner for illustrative purposes.
Okay.
Now, okay, so now why spectrum is thermal? Okay, you can ask this question. Okay, why? How this thermality emerges? For example, Boltzmann suppression. Okay. Now, one of the features of the thermal spectrum is that you cannot emit very energetic quanta. Those will be exponentially suppressed. Okay. And normally we explain for a black hole, for example, we explain this as a Boltzmann suppression. Okay, so there's a thermal state, emits quanta, they are Boltzmann suppressed. Now, this computation in a renormalizable theory gives you exact same suppression, but for a different reason. What is the reason? The reason is the following. If you want to emit very energetic quanta, the quanta with energy much larger than the typical frequency of a Goldstone mode, okay, you have to annihilate many Goldstone modes. But annihilation of the many Goldstone modes is exponentially suppressed. You pay the exponential price because you are considering process many into two. And processes many into two in quantum field theory, they are always exponentially suppressed. Okay? So now an exterior observer, Alice, is observing this bubble that evaporates, and Alice can think that this is thermal state. Okay, because the distinction between thermal state and this bubble is actually 1 over n. So up to 1 over n, this bubble evaporates as if it's a thermal state. I mean, thermal-like state. Okay, so this is what is happening. Okay, but of course, at the end of the day, the state is pure, and the purity of the state is encoded in 1 over s corrections. Now, 1 over s corrections simply are small, and because they are small, it takes Alice very long time to understand that the state actually is pure. At the beginning, she will think that it's a thermal state, okay? Because to purify the state by observations, it takes very long time. Now, of course, this time scale is connected with the time scale of information retrieval, as we can now see. So, if I take this strict limit, semi-classical limit, this double scaling limit, when n goes to infinity, alpha goes to 0, alpha n 1, and r finite, this limit precisely corresponds to the limit. If you want to make correspondence with gravity, this corresponds to the limit in which Hawking did his computation. Okay, so Hawking's computation translates for this theory as this limit. Okay, so it's a double scaling limit. Now, in that limit, what happens is that the spectrum is thermal, and the resolution time is infinite. But okay, there is no controversy because the mass of the Saturn is infinite. So the radius is finite, mass is infinite. And so it takes infinite time to get for the back reaction to build up. Okay. Now for finite n, of course, the time scale of information retrieval and time scale of purification is finite. And the time scale is given by this expression. So there are two ways to retrieve information from this saturated bubble. So you have this bubble, it carries some flavor quantum numbers, and you want to understand what are the quantum numbers that it carries. There are two ways. So there's a passive way of information retrieval or the active way. So the passive way is to wait until bubble evaporates and then check the decay products of the bubble. Or the active way is to scatter a probe at a bubble. In both cases, there is a minimal time scale required because both processes involve interaction. And interaction is suppressed precisely by this Goldstone coupling. Again, over and over again, we get the same Goldstone coupling entering everywhere. And so the time scale that's why this time scale emerges. And this is very similar to Page's time for this saturated system. Okay? Okay, so now, so far, what we see is that the saturated state in this renormalizable theory, weakly interacting theory, shares correspondence with black hole. What we have to remember, the only thing we have to remember is that the Newton's constant is a Goldstone decay constant for a black hole. Then everything falls into place. There is one more thing I want to discuss. I probably still have like 7 minutes or 7 minutes, something like that. Okay. So another thing of correspondence, which is very interesting, I want to discuss is the spin. Okay. So now, what about the spin? So this is this paper that we wrote recently with Florian Kuhnel and Michael Zamtedeschi. So now we have the Saturn bubble, and suppose we want to give it a spin. So the only way known, at least for us, how to give a spin to Saturn bubble without breaking axial symmetry is to give it a winding number. So basically the spin requires that the Goldstone not only rotates in the internal space, but also winds. So this winding number here is the K number. Okay, phi is the azimuthal angle. Don't confuse with the field phi. So little phi is the azimuthal angle. And so there is a winding number. And this winding number generates a spin, which is K times the Goldstone occupation number. So this is the angular, this is the spin of a black hole. Sorry, this is spin of a Saturn. However, there is a price to pay. Now, what is the price? The price is that winding number comes with vorticity. So basically what happens is that there is a vortex that is piercing through this, through the bubble. Now, the objects in which cosmic string or vortex line pierces through are known, in particular for QUBOs, for example, okay? However, for saturation, this has very important consequences, okay? Why? Because spin cannot be arbitrary. Why? Because the saturated bubble has a fixed size, okay, for given parameters. And if you want to increase the spin, you have to increase vorticity. But the bubble cannot support too much vorticity. For example, vortex energy cannot exceed the energy of the bubble, or the size of the vortex cannot exceed the size of the bubble. So what happens is that if you have a saturated bubble, and if you try to make it spin more, then it will unsaturate, okay, itself. So for a saturated bubble, there is a maximal spin, which is given by this formula. Now look, this is a strikingly formula which is identical to formula for a black hole. This is the maximal spin of a Saturn bubble, and this is the maximal spin of a black hole. So it's m squared times the Goldstone decay constant or the entropy. The same for a black hole. Now, why is this interesting? Because, okay, this is interesting for several reasons, but in particular, you see, microscopically, the spin of a black hole is not understood. I mean, we know that black holes, they have maximal spin, but we don't know why. We don't know why in microscopic theory it is a problem to spin black holes even more. Okay. Now imagine that the Saturn gives the correct information about the maximal spin, because Saturn explains why there is maximal spin, because vorticity happens. And once vorticity sets in, you cannot have arbitrarily large vorticity for a fixed size object, for a fixed size bubble. And so it's really tempting to postulate, to conjecture or to hypothesize or whatever, that the maximal spin of a black hole is also because above that spin, the graviton condensate would develop vorticity, too high vorticity. Okay, so this is the, okay, of course, this is just an idea. I mean, we don't know for black holes, microscopically, we don't really know whether this is true, but it's very tempting to make this assumption. Now, of course, black hole vorticity has some interesting consequences, observational consequences, etc., astrophysically. And okay, unfortunately, I cannot discuss in this talk. So to sort of move towards summary, there are a few points that I want to make. So we have this correspondence between black holes and Saturns. This is not correspondence between different theories. This is a correspondence between very specific states in very different theories. So you have two theories that have nothing to do with each other. This SUN model has nothing to do with gravity, but the saturated objects, they behave in the same way, okay? Now, the dictionary goes through a trans-theoretic parameter, which is the Poincare-Goldstone boson, the Goldstone boson of broken Poincare symmetry. That's universal. That is present in any theory. So that's why it's useful. Now, there's a long list of examples by now that we have for saturated states. They appear in form of solitons, instantons, etc. I want to point out two very briefly. So one is okay, one idea we had is to look for saturated states in exactly calculable models. Okay, Otto Sakalashvili, he had this brilliant idea to look for in Gros-Nivier. And so we investigated. Gros-Nivier is a two-dimensional model, is very popular among people that like large N. What is a prototype for QCD because it's asymptotically free, calculable in large N, and the S matrix is known. And we discovered that yes, indeed, Gros-Nivier, the maximal degeneracy bound state in Gros-Nivier model is a Saturon, behaves literally like a black hole, despite the fact that theory is two-dimensional. Another very interesting candidate is color glass condensate in ordinary QCD. This is the paper with Raju Vanugopalan. So we had this idea that there is a correspondence between color glass condensate in QCD, which is a pretty well-known state, and the saturation, and therefore with black holes. So there we made direct correspondence with black holes between black hole end portrait and the color glass condensate. Okay, so let me move towards the conclusion is that, okay, so what is the message that we're taking from here, right? What is the message? The message is, I want to split into, there are facts and then there is interpretation. So the facts indicate that the black hole properties, the ones that are considered to be most exotic and most mysterious, looks like they are not rooted in gravity. So looks like that these properties are coming from much more general phenomena, saturation, okay? And there are many examples in renormalizable theories, as I said. Now, then there are interpretations. Okay, so this is sort of a fact, calculable, which we can go and check. Now there is an interpretation. So the question is, what can we learn about black holes from here? Okay. For instance, so if these other saturated states, they capture the same underlying physics that black hole has, then of course we can learn a big deal about black holes. For example, we learn immediately that black hole evaporation doesn't have to be self-similar. Of course, I cannot prove that it's not self-similar, but it doesn't have to be self-similar because there is no independent evidence on gravity side. It was just an assumption, and evaporation of Saturons is not self-similar. 1/s corrections break self-similarity. So, for example, that's one thing. And of course, the interpretation also cries for, because all the saturated states that we know, they are high occupation, critical occupation states with soft quanta. They are solitons or bound states. And so it's natural to suggest that black hole is also a saturated state of soft gravitons. And this is what I promised you, the relation with this old idea about black hole end portrait. Again, this is an interpretation part. Okay, let me go to final transparency is this. There are also interesting questions about finding saturated states in many body physics. And here is a simple example of cold bosons, the system with cold bosons in a box with very simple interaction. So it turns out that they exhibit this property of moving towards saturation. So you see here that this is the state where this Goldstone-like degree of freedom emerges. You see that oscillation frequency goes down dramatically, whereas away from this point, the oscillation frequency is very high. This is not yet the Saturon, but it's like a enhanced entropy state, of that type. Okay, this is the rainbow. This is the same state around this state. These are the degenerate microstates in this many-body system. Okay, let me conclude that, of course, there are other open questions, interesting questions, independent from black holes. What role can Saturons play in gravity, LHC physics, the standard model physics, and so on, which are all very interesting. So let me stop here. Thank you very much for interesting talk, actually. Interesting questions.
Thank you. It was very nice, very interesting. So let's have some questions now. And the first is Alexander Wickman. Go ahead, please.
Oh, hi, Gia. Great to see you. It was a very nice talk, as usual, very exciting. I'm just wondering about two aspects to bring this analogy even closer. So, namely, we know that classical black holes, they have this Hawking area theorem that if we basically scatter them, then the resulting stuff will be another black hole, and the area can only grow. And it's a purely classical statement. I'm just wondering, is there any analogy of such a statement for Saturns, like classically speaking? It's one thing. And second thing is probably very related, is how to properly define the size. So you mentioned this information horizon. I'm very, very curious how to properly define it. Thanks.
Yeah, no, thanks very much, actually, for important. These are important questions, indeed. So first thing about the formation of Saturn in, let's say, in a scattering process, and formation of a black hole in a scattering process. Now, of course, gravity has this proper. So when you have a Saturn in a theory, another question that you can ask: what is the spectrum of Saturns in a given theory? Okay. So, for example, you can have a theory which only offers one particular Saturn at one particular energy and one particular size. Okay. Now, or you can have theory which offers spectrum of Saturns. So in the theory that offers spectrum of Saturns, the way it happens is very similar to what you said about black holes. So for example, in the theory in which I can have two Saturns of mass m1, m2, and the third Saturn of mass m1 plus m2, what will happen is that the merger will create a third Saturn, okay? For gravity, this is for free because in gravity, black hole spectrum offers essentially continuum of black holes with arbitrary masses. That's why for gravity, whenever you merge two black holes, you get a black hole, okay? For non-gravitational theory, depends on the spectrum. If the Saturn with the right energy is available, it will form. Now, the simple physical argument for that is very simple, because the Saturn always saturates bound on unitarity in any particular scattering process. So it means that if you arrange kinematically parameters in such a way that the center of mass energy is given by the mass of the Saturn, then you cannot form anything else. Why? Because Saturn it essentially excludes any other state. It exhausts all possible states that you can have within that size. Okay, so that's why inevitably you form Saturn with probability very close to 1. But again, for this it is important that the spectrum allows you to have specific Saturn in that place. Okay, and I hope this answers the first question. And the second question was, you were asking about, sorry, I forgot the second question.
I was asking about information horizon, because to talk about area theorem, we would like to know area of what. So what is in black holes? It's clear how to define horizon. I mean, in classical black holes, but how to define a horizon for a Saturn?
Well, it's the same thing. I mean, I showed you explicitly. So the Saturn, the information horizon that Saturn has, and also you have to be very, very careful, both in gravity and for non-gravitational theories. Horizon is a semi-classical notion. Therefore, horizon, you can only speak about strict horizon in semi-classical limit. That's a very special limit. So in Saturn, this limit in which I have horizon is this double scaling limit. When n goes to infinity, alpha goes to 0, alpha n fixed. Then you have a classical solution with a fixed, well-defined size, and that size sets the horizon for Goldstone modes, and correspondingly for quantum information, which is locked inside the Saturn. Once you depart from strict semi-classicality, meaning that if you take n finite, there is always a leakage of information. For the case of Saturn, this is what Talmay was talking about, exponentially small leakage. Actually, leakage is not exponentially small, it's 1 over n. So there is a 1 over n leakage for any finite n. Now, for black holes, I expect the same thing. I expect that for black holes, for finite entropy, there is a leakage 1 over the entropy, or for the 1 over the entropy, not exponent minus entropy. That second part is a speculation. That's it. That's an interpretation. But for Saturn, we know that that's what is happening. Does this answer your question?
I think so. Though I don't properly understand just very simple thing. If you take a classical object, for black hole, in exactly as you said in semi-classical setup, we exactly know what horizon is, because there is unique solution and it's kind of well-defined concept. But if I take something exponentially decaying, usually it's a very vague concept. I could move by factor 2 somewhere. It's not like sharp. It's very seldom sharply restricted position, you know, or sharply restricted configuration. Usually there is some tails and so on. For black holes, there is no such case.
No, I understand. So in semi-classical limit means that you are taking n to infinity. In semi-classical limit, in semi-classical limit, black hole has semi-classical limit is zero back reaction limit.
Yes.
If we define semi-classical limit as zero back reaction limit, then in that limit, the entropy of a black hole goes to infinity. Correspondingly, any correction 1 over s or exponent minus s, any sort of back reaction on a black hole is zero. Now, the same thing, now I'm saying, the same, in order to compare with a black hole, you have to take the same limit in order to compare apples with apples. We have to take the same limit for Saturns. Once you take that limit for Saturns, everything is well defined. There is a unique relation between radius, information, entropy, and everything. So why are you saying that the relation is fuzzy?
No. You see, I was just wondering, how does this solution look like? Where exactly to put this radius? That's very, very primitive question actually.
But the radius is given precisely by the place beyond which you don't get any Goldstone, any flavor content of the Goldstone.
It's a classical solution, so basically it's defined in the same way, but roughly.
Exactly, yeah. It's a classical solution, and you know precisely where that beyond what place any perturbation of Goldstone cannot propagate. So that's what I would call information horizon.
So where is there's a mass in a sense?
No. Maybe what? Okay, I think what you're asking is very important, because look, what I want to make the following very clear. Here I'm talking about information horizon. Okay, so there is a particular form of information, flavor information, encoded in flavor quantum numbers, and this information is carried by Goldstone modes. Correspondingly, the horizon concerns that flavor information only. Obviously, if I have a Saturn and I bring a particle that doesn't interact with the Saturn, this particle can simply go through, obviously, because I mean, we are not in gravity. Of course, gravity is special because gravity interacts with everyone. So from that point of view, this is not a universal horizon for any particle which doesn't carry any SUN quantum numbers, etc. This is a horizon for information, quantum information, encoded in flavor, which is the dominant part of quantum information. Actually, the rest of quantum information is measure zero. So that's what I call horizon, and that is well defined. Okay. Now, on the other hand, what you mean is that because the classical solution has some shape, you are asking whether you can define size precisely.
Exactly.
Yeah, no, size is a matter, could be depending what you are looking for. Size is a matter of convention. But what is well defined is that in the semi-classical limit, in double scaling limit, for example, a scattering amplitude reaches a black disk. Size of that black disk is well defined, for instance, okay? So depending what you are looking for, you can define it very, very precisely.
Okay, I think now I understand much better. Thanks.
Okay.
Very nice.
Okay, next question. Next question is Jamie Cartine. I'm not
yeah.
sure.
Right.
Okay, go ahead, please.
Hi, thanks for the very nice talk. It was super interesting and very
Thank you.
entertaining at the same time. So it was very engaging. So my question is probably somewhat related to the first part of the previous question. So is there any way to, let's say, on the interpretation side, figure out if the spectrum of Saturons could be related to the spectrum of gravitons? So basically, in flavor Saturons equal in flavor, quantum gravity.
Actually, that's an extremely interesting question. In other words, so answering that question, of course, takes us beyond what I restricted myself in this talk, because what I tried to focus in this talk, I said, I'm not trying to establish full correspondence between the theories. I'm trying to simply, I'm satisfied if I have a very different theory here, another different theory here, and I find states that miraculously behave the same way, okay? Now, the question is, and that's an extremely interesting question, whether we can enlarge the mapping neighborhood on the flavor side, so that we enlarge the theory and we try to map it so that it covers more states, more saturated states, some part of the spectrum, part of the amplitudes, etc., etc. So one way I know how to sort of manufacture this type of to enhance this region of correspondence is to, I mean, it's a straightforward way to bring copies of theories. In other words, you have SUN, then you have an SUN prime, SUN double, and arrange their parameters in such a way that they can have larger space of Saturons, and then try to imitate the spectrum of graviton spectrum or gravitational spectrum, etc. Now, one special thing about gravity, which usually at renormalizable theories they do not have, is that gravity is universal, obviously, and this universality is, I mean, is more important than one can naively think. So the fact that every particle, doesn't matter whether what are the quantum numbers, they experience redshift near the black hole, etc. This, of course, plays into the fact in defining why gravity is what it is. So, of course, so that is a limiting factor when we try to map on Saturns in renormalizable theories, because renormalizable theories, they are universal, but only for the subset. For example, if I have gauge theory, of course, gauge interaction is universal, but only with respect to ones that are transforming as representation of that gauge group, or the Goldstone boson. Interaction of the Goldstone boson is universal, but again, only with respect to those particles that carry symmetry, the broken symmetry, and so on. So so there are these limitations on that road, certainly. So right now, I don't know how far one can take this, I mean, this full thing, but certainly I fully share what you are saying, and it's an extremely interesting question. Yeah, thanks a lot.
Yeah, awesome. Thank you.
Thank you.
Okay, thank you. Any other questions from the audience?
One quick question. It seems to me that the analog of the mass of the black hole is the global charge on that bubble.
Yes, that's right. So in other words, yeah.
But
you mean here? Yeah. You mean for the spin or just in general?
No, in general. I mean, you had it even in the previous example.
Yeah. So the mass is this. And the global charge is the, so the occupation number of the Goldstone modes. So the quantum, in the quantum language, we have occupation number of Goldstone modes. In the alternatively, you can think of it as a global charge.
Yeah.
Yes. So in other words, the mass is proportional to the occupation number of the Goldstone modes, and correspondingly is proportional to the global charge. That's absolutely correct. Yes. Mm-hmm.
One thing is odd. I mean, if you try and add global charge, then you'd feel some kind of repulsive forces.
The problem is, so no, you can certainly, so the way this spectrum is distributed, as you can see from here, that it depends, the energy depends on the global charge, but it also depends on the radius and the mass.
Right.
So when typically what happens is that if you add more global charge, the size also changes. If you fix other parameters and you add global charge, you also change the size of an object. And but then it not necessarily will be it will remain saturated, because saturation is a very special point among the relation of the global charge, of the size, and coupling constant. And so if you take a saturated bubble, a saturon, and then try to increase its global charge, it's not obvious. Actually, it's not even true. It's not obvious that it will move into another saturated bubble. So this is related with the previous question about this, how to map the whole spectrum. So, so in other words, so from that point of view, gravity is different, because gravity, if you add mass, it just simply will increase a black hole. So gravity has a black hole for every occasion. There's no problem for gravity. So it can give you a black hole for arbitrary mass. Now the generic theory, in particular this simple theory, will not give you a saturated bubble for arbitrary size and arbitrary mass. It's a very special state. Okay, but you can move away from that theory, and this is what basically was also part of the previous question. And in more general, in more complicated setups, you can have situation when you have the whole spectrum of Saturn. So, for example, if you increase mass or a charge, you can increase Saturn, and you can go from one Saturn to the other. Okay, more like black hole type behavior.
Nice.
Okay.
Yeah, thank you.
Thank you.
Okay. Any other questions? Well, I did have one very simple question, maybe almost naive question. At some point, you mentioned that color glass condensate can be interpreted at least as a Saturon. If it were sort of very similar to the quasi-classical configurations like black holes, one would naively expect that its lifetime is quite long, and in that case you have some kind of like quasi-classical solution that exists for a while. There are these arguments that in heavy-ion collisions we go through this stage of color glass condensate, but it doesn't seem to exist long time, so it doesn't seem to be any quasi-classical or long-lived state. So is there a contradiction?
No, actually, yeah, this is a very good point, and thanks for giving me the opportunity to clarify. Now, the thing, this proposal that we have with Raju and myself. So basically, the proposal there was to directly relate with the black hole M portrait. So basically, to think of similarities between color glass condensate and the graviton condensate in black holes. Now, the thing is that so the time scale, of course, is short for ordinary measures, but the time scale on which the color glass condensate decays is actually given by this page-like time, which is given by n times the size of a condensate. Now, of course, condensate is not a one localized object in that case. There is a gluon condensate. So what do we when we talk about entropy, we talk about entropy per de Broglie wavelength, per de Broglie volume. So we have a condensate, we single out the de Broglie volume, and we treat this de Broglie volume as a saturated object. And so that de Broglie volume, everything indicates that it indeed lives longer by factor n, by powers of factor n. And therefore, yeah, so of course, in real QCD, n is not terribly large, obviously. Because,
so n equals 3, basically, you're saying that doesn't give you much.
Well, it's not, n is not precisely 3, because when I'm saying n, I'm talking about occupation number of gluons.
Okay.
Not about color.
Oh, but that is 1 over coupling constant, so that should be large.
Well, it is large, but it's not like infinite. It's not like in large n QCD, which is much clean. In large n QCD, or in this theory, large n, I can take it much larger. So, so yeah, that is large. Yeah, exactly. So that's precisely our point. That what we showed in this paper is that the lifetime essentially recovers these thermal timescales of thermalization and timescales of decay. They are indeed large, enhanced by n, by occupation number of gluons. And so yes. So when I said that occupation number is not terribly large, I was comparing to a black hole, because if you take black hole of 1 centimeter size,
occupation number of gravitons, if you interpret this as graviton condensate, is absolutely enormous. It's like 10 to the 66 or something like that. Of course, I mean, in real QCD, you don't have such a high occupation number, but of course, saturation is the line. And in principle, you can take alpha to be arbitrarily small and have a saturated state around that alpha. That is, of course, possible. So from what we are observing is literally the same physics in color glass condensate as it is in this understanding of black hole as a graviton condensate. Yeah. So it's very interesting.
Okay. Yeah.
Mm-hmm.
Okay, thank you. I don't see any other raised hands, so I would like to use this opportunity to thank Gear again for a very nice presentation.